Okay, well, should we start there? I don't mind doing that. So I've done a really low-tech sort of scribble. You've got three sorts of radiation, remember. You've got alpha. This one's alpha, and it's a helium nucleus. And the way you're going to try and remember it is that it's 4-2, and then we're He. Okay, so that's what you can write for alpha radiation all the time. And the alpha particle is low penetrating, so it doesn't travel very far at all, but it's highly ionizing. So it causes a lot of damage. It gives a lot of energy to anything that it hits. So it doesn't go very far, but anything it does hit causes massive damage too. Right, the next one, so your second one is beta, so the A, B, and then weirdly it's a G for the last one. So alpha, beta, second one is 0, -1. It's a bit weird, this one. And the -1 is also here. So this is a minus because it's an E-. It's an electron. So your beta is a fast-moving electron. It's got lots of energy, and it sort of crashes around, causing carnage. Now, it's much smaller than an alpha particle, so it doesn't cause as much damage when it hits. But at the same time, hi, everyone who's getting involved now. It's good to see you. The beta particle, when it does hit, will cause a little bit of damage. It's still ionizing, it's still high energy. But what it won't do is quite as much harm as this helium nucleus at the top. But it can travel much further. And then lastly, we've got our gamma wave at the bottom. So this guy has got 0, 0. He's a bit weird. He looks like a fish, so a fish swimming downwards. And he's pure energy. So there's nothing going on here other than just energy on the move. It's also a type of electromagnetic radiation. We did that last year. And this chap, he is ionizing, so it still causes damage, but it's not as bad as beta, and it's definitely nowhere near as ionizing as alpha at the top. But because it doesn't really do very much, it will travel a really, really long way. So some gamma rays are reaching us from the sun. Some of them are coming in from outer space. They're miles away. Loads of travel distance on these things. So there's your three types of radiation: A, B, G. Alpha, 4-2 helium. Beta, 0, -1. A fast-moving electron. It's important you say fast and not just electron if you get asked. And the last one is gamma, and it's just a wave, this one down here. Okay. Hi, George. How was that for you? Is that okay? Hi, Joel. You're a bit late on this one. You could have done with this last year, mate. Okay, so you've got alpha, beta, and gamma. There's your three types of radiation. There won't be any questions on X-rays or ultraviolets or anything like that, because it's on last year's spec, and it's not nuclear radiation. They're on both higher and foundation. You might be asked to do something slightly different. Higher tier students can be expected with these numbers. They can be expected to maybe do a little bit of maths with those in balancing some equations, but on both higher and foundation for you, Lucas, okay? What can I say? Still same old Wilkins. Right, so something else I was going to do, I was just going to talk you very quickly. It's only really a good opportunity to go through some basics doing this evening, but it's better than doing nothing, right? So these are motion graphs right from the beginning of year 11. So this particular bit here, this is a distance time graph. And what we've got is time along the bottom, so that's increasing this way, and we've got distance up the side. And on this one, the object is increasing its distance over time. So it's obviously moving, and it's moving at a constant speed. We know that because the line is nice and straight. We then reach a point here where it stops. Okay, so you can see how it's no longer moving up or down, so it's not getting any bigger or any further. And then lastly, we've got another increase in distance here over time. And again, we've got a nice constant one here. You can tell something extra from a distance time graph. If this is really steep, you know the object is moving really quickly. If it's not moving very steeply at all, then it's not moving quite as quickly. Watch out for this as well. If you've got a line heading down, this means the object is moving backwards, okay? So that's a distance time graph. There's a couple of things that we can do with them. The most important from here is we can work out the speed. So if you draw a cheeky triangle on it, you've got time here. This is harder than it looks. And you've got a distance there. So we can do speed equals distance over time, which some of us have been doing since year 9. Some of us are new to. Okay, so this is speed equals distance over time. I don't know if it looks the right way around on your webcam, or sorry, on your screens or not, but to me, everything looks like I'm looking in a mirror. Okay, right, and you can see underneath I've got another one here. So this is a velocity time graph. And at first it looks exactly the same as a distance time graph. The only way you'll be able to tell the difference is by reading the axes, obviously. Now, something different is happening here in the motion. So the object this time, it is moving away from the beginning, but this time it's telling us that the velocity is increasing. So what does that mean? That means it's speeding up. Along here, it's tempting to say that the object has stopped, but it hasn't. It's stopped speeding up, but it's still moving forwards through time. And then again, we've got another bit here. So from this graph, we could do velocity from a distance time. From this one, from a velocity time graph, we can do acceleration. So this change here, so just like we drew a triangle here, we can do another one down here. This one down here will allow us to find the acceleration. Hi, Curtis, you're a bit late as well. You could have done with this last year too. We could do a change in velocity divided by time along here, and that will tell us the slope, it will tell us the acceleration of this bit here. The steeper, the faster it's accelerating. Then obviously here on the flat bit, we've got no acceleration, we've got no change. So obviously you can see how that works there. Okay. You won't be doing this in year 8. You might do a little bit of speed, distance, and time in year 9. This is GCSE revision though, so you are like 4 years ahead. We can do something else interesting from here as well. It's not just the slope. We can find out how far something went. I'm just going to draw some stuff on here. So it says on the formula sheet that you can work out the distance traveled by working out the area underneath the graph. So on this one, this is a triangle. So from your maths lessons, the area of a triangle is a half the base times the height. So if you worked out what that was, if I had any numbers on this, we could then times those together and divide them by 2. This one here, the middle bit, is a nice rectangle. That nice rectangle is just base times height. And then we've got another rectangle, and we've got a triangle there at the top as well. So you just work out what all of those were. If you're doing a higher tier paper, you might be expected to work out maybe 2 or 3 sections. If you're a foundation tier student, you're probably only looking maybe at working out 1 or 2 simple calculations. They might ask you between this point here and this point here, how far does it travel? And that break it down, make it a little bit simpler for you. Okay. Has anyone got any questions that they'd like to ask about distance time graphs or speed or velocity time graphs? Just let me know before I move on, and I'll do something else. This bit here, this line here on a velocity time graph tells us that the object, whatever it is, a car, bicycle, whatever, this object is moving at a constant speed. So there's no change there's no acceleration, there's no change in motion at this point here, okay? Is that the bit you mean, Robbie? Hi. Nice to see you, Marcus. Again, you should have been here this time last year. The dotted lines, Morgan, were just breaking up the different sections of the graph, helping you read the where you've got rectangles and triangles. Okay, so if we go back to the nuclear stuff again, helpful, I think, sometimes to go forward and backwards. So we'll just remind ourselves, this is an alpha particle, so it's a 4,2 He. This is a beta particle, it's a 0, -1, and an E. This one's your fast electron. This one is your helium nucleus. And then the car stops. Hang on. So when the car stops moving, This is the bottom of the graph. Yes, sorry. I'll go back on that one. So if we've got a velocity time graph here, if the car continued and did from here to here, it would be stopped at the bottom, yes. So it would reach 0, so it would be stopped. Okay. So quickly, alpha particle, beta particle. We can use these to do equations like this. So I hope this looks like a U to you guys and not an N like it looks to me. So this is uranium. Now, some elements are unstable. Uranium, thorium, plutonium, some bits of nitrogen, sorts of big atoms tend to be unstable. There's too much inside them. They're not put together quite right. Because they're not quite put together right, they want to change. They want to make a change so that they can become a little bit more stable. And what they can do is they can do two things. They can do alpha decay, that's the helium nucleus. They can do beta decay, that's your fast-moving electron. Or they can do gamma, which is where they lose just pure energy. So if we have a look at this particular example of an alpha decay, we're going to start with uranium. Now you can see this is the mass number, so this is 238. That means there's 238 things, so protons or neutrons added together inside the nucleus. That's the very middle of the atom. We're not even interested in the we're not even interested in what the electrons are doing around the outside. So all of that stuff that you've done with Blench and Rourke, where you're looking at the shells on the outside, sack that off. We're not interested. We're just on the inside. So 238 in the middle, 92 of them are protons. This is known as by physicists as the proton number. The chemists will call it the atomic number, and they're about the same. So they work the same. This is how the periodic table is organized. So they work similar ways, and it just tells us what's on the inside. You might have done in chemistry working out how many neutrons you've got inside an atom by taking this number away from this number, and whatever's left is the number of neutrons. So this is an isotope of uranium. An isotope, remember, is one of the combinations that kind of fits together. So all uranium will have 92, but some isotopes you can have 238, 235, 236. There's a variety of different isotopes that you can have. 238 is a particularly unstable isotope. Can we leave Morgan alone on the chat for me, please? Okay. If this isotope is unstable, it wants to lose something from inside. In this case, it wants to lose an alpha particle. You're not expected to know that. You just need to deal with it. They will tell you in the question what to do. So all I really know is that it's an alpha decay. So all I'm going to do is I'm going to write this down, probably written for you in your exam if I'm honest, and then I'm going to add my 42He just from before because alpha nucleus, remember, and I'm going to leave a bit of a blank here. And all I have to do here, I need another 234 of them here to add up to 238 on this side. Same's true at the bottom. So I've got 2 here, and we'll need 90 here to get up to 92 over here. So these that you'll start with, you can then work out what's going on. Now, because I know and I prepared in advance, I know that 90 is thorium, and I've just filled that in. You might find that the thorium bit is written for you in your exam paper. You might find that this number is missing or this number is missing. Maybe 2 of them will be missing, but they'll expect you to then fill in any blanks that are there, okay? Right, Robbie, so what you'll probably do is not have all it blank. You'll probably have maybe 92U, and then 234, and then 42, and then this one and this one here will be missing, okay? And what you'll have to do is then write in the number you like there and the number here. I don't know what they ask you to do in chemistry. Perhaps you've done it where you have to balance an equation, and they've actually given you most of the equation, but there's like bits missing, and you just have to add in the missing number of moles or the O2 bit, something like that. So you won't be expected to do the whole thing with a blank space really and just go crazy in it. You'll be given a bit of help to go with that. Just make sure those numbers balance and you'll be fine, okay? Has anyone got any questions before I move on from there? I've got, or I wanted to talk to you very briefly about some car safety, and then I was going to do some Newton's laws, and that'll take us to half an hour, which is about the limit of my attention span. I don't know about you guys. Any questions? Okay, so if we take a look at car safety, so the important thing, there's two things that we need to do. We need to reduce the force on drivers, and we need to reduce the amount of energy. We need to reduce the amount of energy that's transferred into the driver or passengers. So if we think about a collision, Newton's second law, which I'll do a little bit more in detail in a moment, Newton's second law tells us that the size of the force is equal to the mass times the acceleration. So if we make a large acceleration or deceleration, so maybe crashing a car into a wall, we're going to have a very short time, a very large acceleration, and therefore a really large force. So what we want to do every time we have an unfortunate car accident, we want to make sure that the collision time takes as long as possible. And if the time takes it's a long time, then it will reduce the force because the acceleration will get less. So crumple zones are designed to fold up. So instead of there being a big sharp bang, you get a bit of a crunch, and that just reduces the size of that force. It's the same answer over and over again. So seatbelts are exactly the same. The seatbelt, as it's across you, it stretches out in front of you, and that just gives you a little bit more time to slow down, and that reduces again the force acting on you, and just reduces the damage that your body will take as a result of the collision. The same is true. So on the side of the roads, the crash barriers, you might have seen crash barriers on the motorway that have been hit by a car. They get bent inwards, and they're not hard. People think that because they're metal, they're going to be really solid and they're not going to move in a crash. It's the opposite. They're actually quite flexible. Now, obviously, if you go and kick them, they're not going to move. But if you drive a car into them, you'll see that they bend quite a lot. There's a lot of give in there. And that's, again, to reduce the time, to increase the time, to reduce the force within the collision. Other car safety features, airbags do exactly the same. They inflate very quickly, and then as you hit them, you've got a nice slow stop. Hi, whoever you are that's desperate for me to say hi to you. You then have other sort of passive safety features. So they're active. They deliberately stop you from experiencing harm by reducing force. We've got passive safety features as well. So things like on your steering wheel, you've got like the radio controls for the radio and for certain functions that your car will do. All of that sort of stuff is to do with making sure that you spend as much of your time possible looking forwards and not fiddling around under the dashboard, not messing around. Everything like ABS, which is about reducing skidding on the road, so it reduces the chance of having a crash. It doesn't keep you safe if there's a crash, but it means that you're less likely to have one. So it is a safety feature. It's a different type of safety feature. You might get asked about those. If you do, you're most likely to be asked about the reducing collision impact, so reducing the force the passenger feels. And that's the same answer I've given before. It's the increase the time, decrease the force. Could be a nice 6 marker on that. Might ask you to talk about 2 different car safety features. Who knows what they're going to ask you to do, but that could well be it. You might be asked to talk about something a bit odd as well, maybe to use your knowledge, maybe interpret a little bit of text. I was talking today with some of my students about the glass that they use in car windscreens. If you break that, it doesn't shatter into long shards. It sort of disintegrates into teeny tiny little squares. Little things like that all add up to help keep cars safe in collisions. Okay. Anything in particular you'd like me to do on car safety? Do you have me tomorrow, Callum? I don't know, if I'm honest. Hi, Phoebe. So if I've not got you, Callum, I'm sure we can find an opportunity for you to bob in. I think I have got you tomorrow, actually. I think I've got you period 5 or something tomorrow, isn't it, I think? Don't know. Any questions on road safety? Okay, so I'll crack on with Newton's 3 laws then, just to finish off. So Newton's first law is also known as his inertia law. The inertia law is the law that says that an object with mass wants to stay moving if it's moving, and it wants to stay not moving if it's not moving. Yeah, you can come and see me if you want on Wednesday. It's no problem, Robbie. So the inertia law is the one that says it'll stay moving if it's moving. Now, that's an interesting one, because if you want to change the way something is moving, you need an external resultant force. So if you want to make a football move, you have to come along and apply an unbalanced force to that football or whatever. So a large force in one direction that's not countered by one in another. So Newton's first law says that it's basically that inertia. It's that things will stay still if they're still. Things will stay moving with a constant speed, with a constant speed and a constant direction. So if you want to make something change direction, if you want to go around a roundabout, you'll need a sideways force acting on your car. And then the second law is nice and easy, this one. That's F equals ma. Who cares what the words are for that one? I forgot them years ago. Force equals mass times acceleration. And then finally, we've got the third law. Now, the third law can be a bit of a mess, but it's really simple. Just remember, every force experiences an equal and opposite force on another object. So at the moment, if we talk about my two hands, this hand is pushing this way on this hand. And as it does so, this hand pushes back on this hand, okay? So they are a pair because one's this way and one's this way. So pairs have to work in opposite directions, and they have to be the same size as each other, and they have to be on two different things. So this hand and this hand on each other. Some people get a little bit confused sometimes, so they talk about their weight pushing down, and they talk about the floor pushing up. Now that doesn't work because that's a push on the person, and the weight is push or pulled down on the person. So you've got two forces on the person. It's confusing because they are the same size and they are also in opposite directions, but they are on different things. Your downward weight is balanced. The third law pair is the pull up on the earth. Okay, so the earth is pulling you down and you are pulling up on the earth. And you don't think you are because the earth is massive. And that confuses people a little bit. Okay, so just try and remember those simple rules. Same size, opposite direction, two different things. Okay, and that's Newton's third law pairs. You're likely to get some maths around forces. They might ask you to calculate the size of an acceleration using Newton's second law. They might give you one force, maybe say the force upwards on a bag with something in it. And they might ask you what's the force downwards on the person holding the bag, right? So you can then work those out by looking at the equal and opposite thing. Okay, Morgan, I am not going to go over what we did in today's lesson because this is designed as a GCSE revision session. Okay. Right, yes, a resultant force, Henry, must be an unbalanced force because it's the result of what's gone on. If I've got a 10 force and a 10 force this way, they're going to cancel each other out. There'll be no result. It'll just be zero. But if we've got, say, a 20 in this direction, so 20, and we've got 10 in this direction, there's going to be a resultant of 10 in that direction. Okay, so you would see a resultant, and that would also be describable as unbalanced. Those unbalanced or those resultant forces.
The resultant of two polynomials is a polynomial expression of their coefficients, which is equal to 0 if and only if the polynomials.
Can you hear Siri talking over there?
Equivalently.
Shush.
Sure.
He wants to join in. Okay, so we've got different forces. We've got 20 and a 10. The resultant force will just be 10 because it's the two taken away from each other. Okay. Okay, so that takes us to half an hour, 5 minutes of which is me sort of like scratching. Yeah, he should be, shouldn't he? It's me scratching my chin at the beginning, waiting to work out how it all works. You do a huge favor. Can you give me a like if you think this has been useful this evening? Maybe leave any comments. I'm going to try and do exactly the same tomorrow evening. We'll do about 15. I'll have some more amazingly drawn diagrams ready to go. And if you've got any questions that you want me to ask, come and find me sometime during school, or wait and ask them tomorrow evening. Okay. I hope it's helped, and yeah, goodbye from my dining room. I have no idea who the random fox is, but he seems to be enjoying himself, so that's all right with me. You're welcome, Robbie. Anytime, come and find me. Thanks, everyone, and hopefully I'll either see you again tomorrow or take care if you're just passing by because you're one of my old Year 11s. I guess we've got Assembly Morgan. I don't know what we usually do on a Tuesday. Have a good one, everyone. Good night.